Welcome to the course Algorithmic Design. Okay, I would like to quickly show you how classes work. And to do that, I will just go here, I can just say Python classes. Okay, there's this docs Python, docs.python.org. This is the official documentation for Python, and then kind of very, very long text. They explain kind of step by step, but I just need it here for to take out syntax. So here it is. I will just quickly paste it in here. Okay, but this seems to be okay. And I don't even need Rhino for this, and I need to just okay. Okay. Okay, so this is basically how we build up a class in Python. Okay, so just like super quickly, objects intro in Python. I can actually just copy this text from above R. So we define a class. This means class of object class, so it is like a container for an object. And then we can define a name. I mean, here I'm just kind of this is obviously a complex number. There's a complex number and it has a real part and an imaginary part. But for example, we can have something like, particle. There's some particle. So it's not really a point, but it is like a moving point. So we need more information than a vector. Or so if you're, for example, defining a particle, we need a position and maybe movement vector, or so the velocity. So we cannot use a point, and we cannot use just a point, and we cannot use just a vector. We need to basically combine vector and point in order to get to define what the particle is. And we first, at the beginning, we say class particle. So this is the name this will be sort of the name of the class from which we will create instances of this class. So the individual objects will be instances of this class particle. And in Python, the convention is that class names have they start with the capital letter, or that's why we write here with the capital letter. But you can also just write a small one, but that's very, very bad. It's against Python style lines or Python style. So please always use capital letter. And then the first one that you always need to put, and it's a bit confusing, it's like def init, or so it is the initialization method, and it's a bit you can't really see it here, but it's like underscore, and it's just a syntax thing. So we need to put it in. So it needs to be 2 underscores, init underscore, and then self goes at the beginning, and then we have parameters. So for example, position and velocity. Okay, and that's another, with classes, that's another kind of thing that they could have maybe filtered out. So this self needs to go at the beginning always when you, so this is called the method of the class, like internal function. And we always need to pass the object itself into the method, and that's this self. Again, here you can actually write whatever you want. You can write kind of Luka, but again, the Python style or style guidelines, the convention is that you use self to refer to the object itself from within the object. Yeah. So that's just the name that we use. Okay, and then this will be run when the object is initialized at the very beginning. So we need to create attributes. And then if this is the name of the object self, then the attributes is self dot, and then we give it a name. For example, pos equals position, and self dot, for example, velocity equals velocity. Velocity. Okay. So of course here we can. Yeah. So again, here you can you basically just go from parameters here into the attributes of the objects. So you kind of just basically rename them, you store them inside the object. And for example, for a particle, this is it. maybe we can add another method, internal method called def, for example, draw or something like that. Okay, so we define a particle, but then we want to also draw a particle, and then maybe we need to load in, import rhinoscriptsyntax as RS. Or actually, I'm just thinking. No, let's keep this. Let's not use Rhino anything, but maybe not draw, but then we can use, for example, move, something like that. Okay, so if you want to move a particle, we can say we need to pass object itself, and then we need to pass some kind of force. Okay, and then self dot position plus equals. So we are going to add force to the position. That's it. Is that correct? No, wait, actually, I'm just thinking velocity. Yeah, it's actually, let me just see. There's going to be move. Move is actually, position plus, it's not force, but we add the velocity to the force, or sorry, velocity to the position. Okay, and then that's it. And then maybe there's also something like def, something like force or something like that. So we can add additional external force to it. Force self dot, and how do we do that? We can actually, or let's actually call it apply force. So in every iteration we can just add, velocity. To velocity we can just add this external force. So not force, just force. Okay, I hope I didn't confuse you here. I'll just delete this top part here, but this is basically, I'll just write here a comment, creating a particle class. Okay, and now, of course, we're not really drawing anything yet, but we have sort of, move, and we have some force that we can apply to that particle. So we'll do kind of everything in just text space. Or so here in the main part, we can create, different particle objects. Okay, so we define the class. That's at the very beginning. If you run this, nothing will happen. Or so we just define the class, define this container, but this is kind of ran, but we are not really using it in the main part of the code. So it's like a function that we define, but we don't use. And we need to create different particles. Or so I can say, for example, particle 1 equals, or we'll create a particle instance, or article, and then we need to give it some attributes. This will be, some maybe vector. Yeah, I just realized that we need a, we actually do need to have position and velocity. We need some vectors, or so we are not going to create a vector class now. So we're going to use geometry as RG, and then we are going to add here, RG dot. So the position will be something like 0.3D, and then some position, maybe 0, 0, 0, and velocity will be RG dot vector 3D, and then maybe some vector, maybe vector that goes up. That's it. Okay, so this is now we created our particle. And if I say, for example, print particle 1, if I just run it, it tells me, okay, you created a particle instance at this position, or so this is a position in the memory, but there's a particle instance that is created and it's stored, and we can access it. Or so I can now say, for example, particle 1 dot pos. Actually, let's print all the attributes. Or so pos, and here we have what is that value? Or so I can print out these attributes. So the position, this is the position, and this is the velocity. Okay, so they are now reload. No, okay, so they are now just stored inside this particle one, and yeah, and then I can now I can say something like, well, I want to move this particle, so kind of iterate it. I can apply this internal this method to it, so internal method to it. So I can say particle one dot move, and I don't really need to pass. Here's a force. I don't need this. Okay, so when I'm calling the method, I don't need to call this self, so the object will be passed automatically. So I can just leave this empty. If I say particle one move, now suddenly I kind of apply this, so this will be ran, this will run, this will run. So velocity will be added to position. So it's like moving a particle. And if I print it again, now I get different values, and I can actually apply this multiple times, and then I'm going to get so now I kind of added sort of this in a way I simulated a moving point, or the point has a velocity that has a z component positive, so it kind of is moving up, so the position in every iteration is a change in the z toward up, or so in a way I'm just adding this velocity to the position. And then just think a little bit. Okay, so now this is a little bit this is maybe a little bit abstract, but I want to create like a super simple example to show you where can this lead to. Or so I basically have more or less a skeleton with which I can simulate a moving particle. And this is now, you kind of think about this is like stupid. It's just kind of adding numbers together. But yeah, it turns out in physics, simulating moving particles is not really much more than maybe multiplication and adding of, in this case, vectors. So let's try to do that. Let's try, if you have Rhino here, we can maybe have some center here, and we can maybe have a particle that starts maybe somewhere here, and then it moves up. It has some, or actually it has some velocity, or it goes up, but it also gets attracted by this attractor here. Point goes here. Okay, so it gets attracted by this point, and as soon as that happens, it starts to kind of move. In a way, it starts to orbit around this point. So when there's attraction force happening, this particle will start. It will start kind of deviating from its path, and that's basically what's happening. That's how kind of Newton used, of course, calculus to calculate these trajectories. Today we know, or we would use maybe a special theory of relativity to, think about gravity as curvature of space-time. So the math is a lot more complicated, but for these simple cases, the or how do you say, the non-relativistic velocities, the results are the same. So if you don't move very fast, we get the same result as Newton. But basically, this particle kind of moves up, and then maybe there's an attraction force that starts happening, and then the particle starts orbiting. And then basically, if you connect this again as some kind of curve, we basically get a particle trajectory basically orbiting. Okay, so we can try to do that very simply, because now we have almost everything we need. We just need to calculate this force. This force is basically, it acts in the direction of the, in the direction of this. It's always acting toward this origin, let's say. Okay, so this is some kind of objects intro. I will save this as attracting particle, something like that. So I kind of mentioned today that I will not really introduce new topics, but here I go. I just want to show you kind of application of this kind of quickly so that it doesn't stay so abstract. Okay, attracting particle. Okay, so there's a particle, we have position, velocity, and let's try to do this kind of, so it makes sense. Just a minute. Okay, so particle is here, particle 1, and we can define it here. So the position, well, we can say something like starting velocity. So let's put this outside. So starting velocity is this vector. And yeah, maybe it is actually going up, or so it will go in every iteration, it just goes up. So this is a positive number here. So the starting velocity goes here. And before that, there's maybe, you know, starting position. Okay, and this is a point. And let's kind of try to replicate this image. So we start maybe, what is this? This is actually, this is 10. So maybe it's something like, maybe we start here. So it's like minus 20, what is this? Minus 20, minus 10, something like that. It's minus 20, minus 10. And here we're working with a flat, in the flat world. So, yeah, actually here, let's pretend that when I say up, I actually mean y positive, or so we don't work with z, we work with just y. So we work with x and y. So in this 2D plane, we don't use a third component. This minus 20, minus 10. So it's somewhere, it's actually here. Put the grid snap here. Okay, so this is where we're going to start. The point will start going up. Up. And starting velocity is like 1. And there's a particle, has starting position and starting velocity. And then just actually, okay. And we can define some kind of number of moves, or so number of steps. Number of steps. So there's not some number of steps, and maybe let's say 100. Okay. And then I can say for I in range, number of steps. So we're going to just move 100 times. I will apply this particle 1. I actually don't even call it particle 1, just call it particle. It's fine. Oh, no, actually, no, let's leave it 2, because maybe we'll have more particles. Okay. Creating different particle objects. There's particle 1, great. There's number of steps 100. And we will apply this move to the particle 100 times. And yeah, actually here, as we are extending this a little bit, let's actually import, you know, rhinoscriptsyntax as RS. Okay, so we're going to apply it. And then we have this move, apply force. Let's extend the class. So we can say def draw. So we want to draw where the position of the point is. You have to pass self. And well, that's actually it. It's just we pass the object itself, and then we can say rs dot. There's a function called add point, and we add the position of the point. So current position of the point will be just added. It will be just drawn as a point. Or so here, when I move the particle, I can just say particle 1 dot draw. Now, of course, you can ask, well, you know, this is very short. Like, why didn't we just use this function here? Like underneath, we could, but you know, maybe we don't really care how particle is drawn. Maybe you know, now we use this add point, but maybe we want to, you know, create a polyline, or we want to create a point cloud or something. So we are just using this function here, draw, or internal method draw, to basically tell the particle kind of display or path or display or position, and how this is handled inside the method will be decided in a way by the object itself. So the object or the class will sort of decide, or a programmer will decide how this drawing will happen. So we kind of in this way decouple, or so this is already an application layer. So we have our object, and there's a draw function, and how the particle is actually, or how the object is sort of drawn, displayed in Rhino. This is handled by the object object itself. Or so we kind of started to decouple a bit, sort of code development and in a way application layer. Or so when you every time when you work with coding and you hear API, API is application program interface, I think. Or so the kind of there's you are using the library, you're kind of, but you're sort of applying the library, or so that you're working on some kind of application of the library, or so some things are happening on different levels. Okay. Okay, so we kind of created sort of our own API here, and we are here just using it. Okay, let's see how this works. So I can just kind of run this. Okay, perfect. So not really impressive. Aha, this is point 3D. Somehow I'm a bit disappointed because, aha, okay, this grid is okay. Yeah, somehow, yeah, this is not really 1. This is actually 10. It has to do somehow the density of the grid changed. So I'll just increase this a little bit by 10 here. Okay, this was unexpected. I think this is because the Rhino operation changed. Okay. Okay, so this is a moving particle, but of course there's no force applied yet. Also here on the top, we can just say rs.enable redraw, and we can put here false. So now it's just gonna this is gonna move a little bit faster. So again, if I move it again, I just get all the results. Perfect. Okay, but there's no force applied yet, but we actually already kind of have our force function here, or there's kind of velocity, and there's this force. And now I hope I will do this correctly. So let's calculate. So before we draw, actually before we do the move, let's try to calculate this. Let's try to calculate this force. Or so, what is the force? There should be some kind of attractor. So force is it is a vector that connects the particle position. Let's see, free. Okay, so it's actually it goes from the origin, or so rg dot point 3D, and actually I think I can just say I'll just put 0, 0 here. Okay, so that's from the origin of the world to particle 1 position. So that's my force vector. And then I can say particle 1, and then I can say apply force. So I can apply that force. And the force is just here called force. And then I move. So I create the force, I apply this force to the particle, and then I move in that direction. I don't really know how this will work. This might be a little bit too strong. So I might actually scale this, or so there's maybe some kind of a damping, factor is maybe 0.1. So I'm going to multiply this force with damping. So it's just going to become a bit smaller. Okay, and yeah, let's see how that works. Oh, yeah. So just a minute, what did I do wrong? 28 here, force vector 3D. Yeah, I forgot. No, yeah, I kind of did this wrong actually. Yeah, I'm trying to create, sorry, a vector 3D from scratch. This is actually wrong. You know, so I can calculate. Yeah, if I just pull out my paint, so I can calculate actually what this vector is. Or so it's I'm just going to draw it here. Maybe a thicker one. Okay. So if I have my origin here, and I have my kind of a particle here, then I have, this is the sort of particle vector. And I have my origin. Yeah, it's actually just yeah, because this is sort of 0, then this vector is basically just goes in this. So it is the coordinates are the same as for the point. Yeah. So actually, I think if I say apply force, I can just say, let me just think a little bit. It is then particle 1 dot position. Actually, forces, yeah, I'll just do it outside. Okay, so it's actually the sort of position vector of the so the point vector, the position vector of the particle multiplied by damping, or according to my amazing diagram that I just did here. That's the force that's acting, but I have to check if I need to maybe flip it, if it needs to go in the opposite direction. Okay, yeah, it needs to go in the opposite direction. So it's like is the negative. Also, cool thing about this, let's actually see if this works. So maybe I can actually put this negative force, it's attracting rather than, okay, perfect. Yeah, so I got basically a circular orbit, or let's increase a bit starting velocity, maybe it's a bit bigger. And if I just run this again, yeah. So it's a bit, again, hard to see exactly what's happening, but I'm starting here, but somehow not drawing this exact point. And then it goes from here, okay. And that now there's, yeah, there's just a particle. Particle is just moving, goes like this, and goes kind of around. And if I change this starting velocity and maybe starting position, I'm basically getting different circular orbits. And these are now just represented as points. Maybe if I have a little bit less steps, you can see it a bit better. Or so if I can start where I started before, 200. Okay, so this is actually the, yeah, actually I can just also draw the particle at the very position. So maybe here I can just draw it, okay. So now I'm gonna get the first point, okay. So this is the movement, or so this is where I start. The particle wants to go up, but it actually gets attracted by this origin here. So it starts deviating from the path, deviating. And I mean, the force here is always the same. It should actually be proportional to the, it should be reverse proportional to the distance. That's be kind of proper gravity. But in this case, we are getting this elliptic orbits. And if I just continue this for a few more steps, I get the same thing, but it kind of course, then goes sort of back and then just continues. So I get, I think, overlapping points here. Yeah, these are these points, they overlap. Also, this is basically an orbit, goes around, and yeah, that's basically that. So this is now kind of an orbiting particle around this origin, and yeah, that's it. So I'm just think a little bit. Yeah, I can, for example, have again a different starting velocity. So now we go up, but maybe we go, for example, we go sort of in, you know, like this direction or something like that. So if I start from here, I should get a bit different result. But in this case, it will always be an ellipse. There's always been an ellipse, and more or less that's the reason also why the paths of planets in the solar system are always kind of ellipses. Not to kind of talk too much about the physics that I don't know too much about, but basically this will be, basically it will always be an ellipse, and under maybe some circumstances it might become a circle, but it's basically an exception, not a rule. Okay, so basically this is now more or less a kind of a particle trajectory simulator, and we have sort of a particle class here. We can create our particle, and then we can sort of apply different forces to them or to these particles. And just to maybe extend this a little bit, it is of course clear that I can just, I can extend this. Let me actually say, let's do a super short extension. So attracting particle, I can, for example, say attracting particles multiple, or sorry, attracting particle system. Okay. So I can just quickly now add more particles here. So this is now easy because I have everything nicely set up. So let's do that super quickly. Create different particle objects. So I can say, number of particles, and maybe we have 100 particles. And then I can say for n in range, number of particles. So everything that I did now for one particle, I will now do for multiple of them, or I can just select them here, do tab, and but now I will have sort of so I want to use a generic name, so there's no particle one, but I want to have a list of particles, or so I can say something like particles equals empty list, and I actually, I can kind of say here particle, when I create it, I can just say particles dot append. I can add them to a list, of course. Okay, and actually here I create them. Here I create them, and just think a little bit. I can have a separate for loop, or so this is creating, and I can say something like number of steps. So I want to decouple this kind of creation. So here they're created, and here I can say for particle in particles. Okay, so I'm iterating through the particles list. Okay, I'm iterating through the particles list, extracting individual particle, and then I'm kind of doing something with it. And here, even though I'm always using the same name, these are now different particles from this list. That's it. Actually, I can just put all these number of steps and everything here. Stamping. Okay, so here is creating different particle objects. It's here, and here is moving all the particles. Okay, so I have kind of two lists doing separate things. Here I just create them, and here I kind of move them. Here I have to change this. So no more particle one, just one. And but now they all start at the same position. They all have the same starting velocity. So that will, what that will produce, of course, they will all have all the velocities will all overlap, which is not that cool. So now I have like 100 points that are all at the same position. If I select them, it's 100 points. And now I want to juggle it up a little bit. So maybe here I can just change a little bit the starting position or so. So maybe the starting velocity is the same. That will change the starting position. I can maybe import, import random. Okay, I want to import a random library, and then here I can just say random dot uniform. Actually, let's see something like random x position is random dot uniform, and then they can start actually anywhere. So maybe some actually let's start from kind of -100 to 0. So that's random x, and then there's the random y, maybe the same. Of course, it'll be the same. It'll be different random number, but the domain is the same. Okay, so now we start at a random position. some kind of negative x and negative y. Perfect. And starting velocity will maybe be the same, even though this we could also kind of randomize. And now we should get a bit nicer result. Okay, perfect. Yeah, there's maybe okay, yeah. Let's reduce this a little bit. So maybe this was fine, or this was kind of fine. And yeah, this is a bit. Maybe they don't start. We constrain them a little bit, so they start somewhere in this corner here, something like that. Maybe 200, 190. Okay, so we constrain the domain. They can now be created within a certain. Okay, yeah, they can be created in this square, and then they just kind of go around this. Maybe again too constrained. So we have small weird. Okay. So now they're all created in. Yeah, it is hard to say where it is. It's between. That's the kind of domain. So I guess it's somewhere here, and then they all start off, and they're all these particles all move in these elliptical orbits. So there's a lot of kind of overlap here because somehow the periods are the same. The numbers of steps is the same, the distance to the attractor is the same, but they start again at a different position. Maybe let's randomize a little bit also the starting velocity maybe. How do we do that? We can actually just put random x or random y also in the velocity. Oh no, actually let's say something like ran vel. So random velocities random dot uniform, and it is again some number. Maybe it's again maybe from -100 to 100, and this random velocities are just a number that is applied here. So some random kind of velocity components. Okay, yeah. This may be random uniform. Yeah, we put this to 0. Okay, actually -50, something like that. Okay, yeah, somehow this didn't work out so well. Yeah, this didn't. Yeah, I think it's because just random velocity x, random velocity y. Maybe this is to -80, and this one is maybe from 80 to 100, something like that. Random velocity x, random velocity y, and then z is just fixed. So it's so if I go into space here, we have a kind of a flat object here. Okay, I'm just trying to get some nice ellipses. But again, I have to it's just about setting the domains correctly. Okay, yeah. So now it's a bit similar to what you had before, but now also the velocity is a little bit randomized, so we have less overlap. But yeah, we have some kind of a stochastic behavior, maybe just 10 particles, so 10 ellipses. Okay. Okay, that's it. So that's kind of the already going. That's basically just simulating a sort of a particle system. So you can notice here that we didn't say anywhere that we are creating an ellipse, but somehow elliptical trajectory came to be because we basically we sort of simulated this attraction force toward the center, and because there's some starting velocity, this will never be 0. Also, this velocity that you're adding here, when you say move, we add kind of velocity to the position, and then here this force is also always applied, so toward the center. this will never even out, or so it will never become zero. This velocity will never become zero. It will kind of, this velocity is sort of a vector that is just kind of rotating in this way. So it is oscillating forever. And yeah, that's a little bit also kind of what is sort of happening in the solar system, and basically what Newton kind of figured out with calculus. He just did all these calculations using calculus and then figured out that these trajectories are all ellipses, and they have to be ellipses because of the force and so on. So kind of what, again, not to go too much into, I guess Galileo figured out that there have to be ellipse, the trajectories of planets have to be ellipses, and Newton basically found a math exactly why they have to be ellipses, and they cannot be any other shape.